Hello and welcome to another lecture. In this lecture we're going to go ahead and design a shear wall. If you look at this rivet model I got, this is actually what we're doing right here. This wall right there, I like to make this a shear wall, and the opposite wall on the other side also make it a shear wall. The building is about 100 feet by 60 feet, and this is from here to there is 30, and the garage door is 20, and then we got 10 foot on the other side. And if we turn around right here, we got right here we got 8 feet overhang. And also I like to design this wall to make it a shear wall. What happened in that we have the earthquake FX force coming in this angle and in the other angle, so that's why I want to make these I lied coming from this angle, the FX coming this way and FX coming that way. So we designed these two walls to make it a shear wall. If you know how we calculate these load, let me go to the PowerPoint for a second. So this is the plan view of the same rivet model. You got 100 feet, 8 feet overhang, and then we have this diaphragm uniform force, which is basically a FX. And you know how we calculate this seismic force, watch my previous video. And this is about 364 pound per foot, and this overhang one is a 280 pound per foot. So we want to design this shear wall number 1 here and a shear wall number 2. Shear wall number 2 has an opening because of the garage door. So anything else is given the moisture contact of the wood is less than 19%. CM is 1, CT is 1, and the door is made of a 2x8 stud, number 2 Douglas Fair large. I think that's about covered, so let's get to work. Load right here, which is a seismic force to roof diaphragm right here, and both for the roof itself and the overhang. The overhang is about 280 pound per foot, and the roof is about 360 pound per foot. If I go ahead and draw this in elevation view, if this is the wall, your earthquake is kind of goes like this, the shear base shear force, and this be your FX, and this will be your V. And if you want to know how we get these, watch my previous video. So anyway, let's come back in here, one of the first thing we want to calculate is the reaction force from this load right here. Let's find the reaction force R1 here and reaction force R2 right here. And this wall right here, let's call this wall 1, shear wall 1, and we're going to call this wall here, which would be kind of like this coming down, and this be a shear wall number 2. So that's the reaction R. And to calculate the reaction, we're going to come back down here, and it's going to be basically 280 pound per foot. The turbotree width is 8, and then plus 364, and the turbotree width of that one is 100. So that's going to be, for the reaction, be divided by 2, and basically it's a WL divided by 2. You know what I'm talking about. So if I come back down here, this is half of this load, half of it going to go over here, and the other half is going to go there. So, but this is a pound per foot, so you got to convert them to a pound, and that's what we're going to do. And this is going to come out to 20.44 divided by 1000, make them keep. And then that's R1. So the wall number 2, it's going to be right here. It doesn't have the overhang, so basically it's WL divided by 2. R2 is WL divided by 2, you know that, and our W is 364, our L is 100 feet, divide that by 2, and that will give us 18.2 kips. So let's go ahead and work on shear wall number 1. Alright, so this is the elevation view of the wall. And what we have here, we already did calculate this load right there, which came from here. And then we take the whole wall, and the wall is a 16 feet by 60, and calculating the wall seismic using a dead load of the top half of the wall. And this is basically using dynamic theory, which I kind of really, I'm not. If I had to do this, I would calculate the entire wall rather than half of the wall. But a lot of designers, the older generation like myself, they use the half, all the wall. The newer designer, which they're kind of more economical and stuff like that, it's not good really, and they basically follow the code, use half of the wall. The dynamic theory, let me go to the PowerPoint and show you something here. Here, and it's basically like, when you have a seismic force, when a building shakes, the weight of the building become liability, become a sideways forces. And as you can see here, the diaphragm right here, they're going to use the turbidity width to be right here, halfway. Anyway, let's go back to the problem. So we're just going to go ahead and stick with the halfway for now, rather than entire wall. Okay, so what we're going to do here is just go ahead and calculate the shear wall number 1. And this is the elevation view of the shear wall. As you can see that it's a 60 feet by 18 feet. And the load that came, we calculated it was R1 was 20.44 kips. And then we have the height 16. And then we're going to go ahead and use half of the calculate wall seismic force using a dead load of the top half of the wall. And this is basically follows the dynamic theory and a seismic code. There we go. So the dynamic theory is basically when a building shakes, you're going to have, you've seen this before, we talked about in class, you have the base shear and you have the Fx on top. And when you're using a diaphragm, with this, we're going to use a roof diaphragm, but in here is going to be example of a third floor. Use basically the turbidity area halfway. Let's go back to calculate that load. Before I do, I'm going to switch PowerPoint here. What we're going to do, we're going to calculate the shear force using right here. V is equal to CS times W. This is the ASCE seismic code, section 12.8. And CS is given to us, and we just got to calculate the load, and we can figure out the shear. Okay, let's get back to work. So we're going to calculate R1U, which is equal the CS times W, and that's equal, and that was given to us as 0.20 multiplied by the weight of the wall. The weight of the wall was 20 pounds per square foot. It's kind of given, and it's 8 feet, and that will give it a pound 8 feet times 60 feet. So that will give us we can divide by 1,000 and make it a kip. So that's equal 1.92 kip. So that's what R1U is. Then if I do summation Fx is equal 0 of that wall, let's go right as positive, we're going to have VU is equal RU plus R1U, which is equal 2044 and plus 192, and that will give us 2236 kip. So now calculating the shear base, small v, it's VU divided by the width, which is 22,360 pound, converting back to pound, and divide by 60 feet, and that will give us 373 pound per foot. Now if we go to ASCE chapter 2, and for the load combination they use ASCE chapter 2, the load combination, this is a load resistance factor design. Let's find the allowable stress one. You can go ahead and look at the chapter 2, find out. There we go. The allowable stress design is right here, and you can see that for earthquake they have 0.7 time EV, and that's where the 0.7 come from. And basically load combination 8, 9, 10, they give you 0.7. Let's go back to work here. Let me change color back to yellow, and therefore we have our V, small v, is equal 0.7 times VU, which is equal 0.7 times 373, and that gives us 261 pound per foot. We're going to use that number. And this problem, it didn't give a lot of information. I think this is the SDS D, and if you want to know what that means, just go watch my previous video we did on seismic force. So basically we have this 261 pound per foot shear. Now we got to go look up in a table, find out if we kind of find a sheeting and what type of nailing that it's going to be stronger to this. So this is basically the applied load. We like to find something with a capacity bigger than this. What I'm talking about, let me go to the PowerPoint for a second. Okay, so now you got these plywood sheeting right here, and that's basically and say the earthquake, this assuming this is top of the roof, which is not, and if the force coming this way, this plywood, the shear capacity of this plywood acting this way, we're going to find out what it is and how much nail spacing we're going to put in here. Let's go work on that. So we're going to go to a table from SDPWS table 4.3a, and look at that table. So let's go to that table. Let me see if I can find it. I don't have that code with me, but we can grab it online anyway. Everything's online these days. Alright, so looking at this table, we're gonna go ahead and use 3/8 plywood sheeting right there, and we're gonna use 6D common nails, and I'd like to go 4-inch on center for nail spacing. And if you come back in here, it says right here apparent edges and spacing 4-inch right there. So if I go 4-inch, my shear right there, it's going to become 600. See if I can highlight that. Oh, I couldn't do it. It's going to be 600. Let me see, right there, 600. You can see it. So our shear capacity pound per foot is 600. All right, let's go back to work. Using this table, so we decided to go with 3/8 sheeting. Oops. With 6D common nail. At 4-inch on center edge nailing. Okay, and our shear capacity equal 600 pound per foot, which is bigger than our 261. So the shear capacity came out 600 per SPSDPWS 4.33. The allowable unit shear should be divided by 2. So if we divide 600 by 2, 300, which is bigger than 261, it's okay. Let's go see if we can see that section I was telling you about. Let me switch here. It's right here. That's where it talks about. That's where it come from. All right, we're going to move on to wall number 2, which I wrote it down. So shear wall number 2, the same code allows us, if you have a multiple wall going across, but they all made the same material, you are allowed to use to be used. So like in here, we have this, if you're looking at the wall elevation right here, we got the doorway and all material the same. So then we have the shear RU at 180 right there, 8.2 kips, and then we have R1U, which is the same as before we figured it out. Then you have a shear down bottom. Of course, you have the opening where the door is, then it picks up on the other side. Let's go ahead and calculate that. Our VU is equal RU plus R1U, which is equal 18.20 plus 192, and that will give us 2012. Then our small VU is equal VU divided by B, which in this case is 120. Let's make it to a pound and divide that by 30 plus 10. We're going to skip the doorway. So we're going to go 30 right here and 10 right here, and we're going to skip the doorway. So our small VU is equal 503 pound per foot, and that's basically the yellow one right here. This we're talking about right this. And just like last time, because of the earthquake, the load combination, V is equal 0.7 times E, which is equal 0.7 times 503, and that will give us 352 pound per foot. Now we're going to go back to that table again. Let's we can find one to beat that. Remember, whatever we pick, it has to be twice because we're going to divide it by 2. I'm going to go back to this table. So look at the column right here. We got sheeting material, you got minimum nominal pound thickness and fastener and nail size. We're going to use wood structural panel, either this row or that row, and then we're going to use a 3/8 thickness for our sheeting, and then we're going to use a 6D nailing, and then we're going to come back in here. Let's go, we want a number that is bigger twice. This number looks good, 780. So that's a 3-inch spacing, and 3-inch spacing for 3/8 down bottom right here, down bottom right there, and that will give us a 780. So that's where it come from. Let's go back to the writing. Okay, change color for good luck, and we say allowable is V was 780, divide that by 2, and that will give us 390 pound per foot, which is bigger than right there, 352 pound per foot. Okay, so we're gonna start with the tension cord, and we're gonna look at this right here. And this is our doorway, and this is our design, and we're gonna look at the tension cord. So we have the shear force here, which is RU divided by B, came out to be 455 pound per foot. And then this was R1U divided by B, which came out to be 48 pound per foot. And the doorway is about 12 feet tall. Then we have the shear down bottom, which we figured out already was 503 pound per foot. And as the movement happened from left to right to this way, and you're gonna have no, the other way, the shear coming this way. So basically, let me do this, and a force coming like this in this angle, and puts this right here in compression, and this go in tension, and again this go in compression, this goes in tension. So let's calculate these. Same thing, we're going to multiply based on ASCE 722, we're going to multiply by 0.7. So we're going to have a load at the top of the shear wall, and we said V was 0.7 times E, or in this case would be 0.7 times VU, which is equal to 0.7 times, or you say 0.7 VU, same thing. 0.7 times 455, and that will give us 319 pound per foot. We do the same thing, load from top half of shear wall. V is equal 0.7 VU, which is equal 0.748, and that will give us 33.6 pound per foot. If we take T is equal C is equal VH, basically is equal 319 times 16 plus 33.6 times 12, and that's equal 551 kips. So now we're looking at the tension in this stud, which is a 2x8, and if we look at 2x8 down the hole, assuming there's a 1-inch diameter hole for the bolt connection, and let's just calculate the net area of that. Net area A is equal 1.5, which is 1.5 times 7.25. Take it back, minus 1 inch, that comes out to be 938 inch square. So now we have that the tension stress, let's go to different color, F of T is equal T divided by AN, and our T came out to be 551, so that's 5,510 pound divided by 9.38 inch square. So we have ourselves a 587 psi. Now we gotta go to NDS. Assuming the wood is a number 2 DFL, and go to table which we done many times, table 4a. We're gonna get these result below. I'm gonna write it quick, and I'm just copying it from the table. Okay, so these are the result, and CF from table 4a. Remember, for tension is 1.2, for compression is 1.05. We did this many times, so I'm not gonna go over it or watch other video. You know, it's pretty simple. Forward, go into those table, figure those out. Now we have this. We're gonna go ahead and find the adjustment factor. Our ASD adjustment factor, F prime T, and that's equal F at T. That's from table 5, no, 4.3 times CD, CM, CI, and CF. And we already have all those value. We're going to go ahead and plug it in, which is equal 575, and CD is a 1.6 for those load combination, and then we have 1 times 1 times 1.2, and that will give us 1104 psi, which is bigger than our 598 caused by the load, and we are okay. Okay, so the 2x8 is adequate for tension cord, and this was just based on this 505.51 kip right here. However, if we consider the dead load also, it should be considered, then we're gonna check into that. And this is where it's gonna get a little bit interesting, because we're gonna go to ASC 722 load. There are 8 for allowable stress design. There are this 3 load combination. Let's go there, show it to you. Right here, chapter 2 ASCE, for allowable stress design for earthquake, you got load combination 8, 9, 10. We got to find out which one of this apply to our case, because we have a dead load and roof life load. And then find out what's EV and EH is. Let's go to chapter 12. That's I know the page number. And right here, section 12.4, it says E is equal to EH plus EV. And then coming back from equation 12.41 to 12.44 right here, 12.3.43 says EH is equal to rho times QE, and EV is equal to 0.2 SDS times D. And we can find rho and SDS easily from the ASC hazard tool. You just type in the location. So let's go back to the writing. We're gonna say, I think this one controls right there. Let me write this down here. This should control right here, just by inspection, or you can do all 3 of them, see what comes out to. So we have T is equal 0.6 D minus 0.7 time, instead of EV we're gonna say rho, which let's assume rho from ASCE hazard tool. We have rho is equal 1, SDS is equal 0.13 G. So we're gonna have 0.7 times 1 and time QE, and then minus 0.7 times 0.2 times 1.3 and time D. So simplify this, our T comes out to be 0.6 D minus 0.7 QE, and then be minus 0.18 D, which is equal 0.42 D minus 0.7 QE. So one thing you want to remember why this load combination control is because the tension is a negative, and you have points minus negative 0.7, negative 0.7, and that adds up the highest. Again, you can try all three of them and you find out this 10 will be number 10 will be the highest. However, when we do the compression side, it's going to be number 8, or you can go through each one of them and figure out. So I'm going to go ahead and go to the compression side. We're going to say, let me change color for good luck here. Compression is equal, it's going to be 1D plus 0.7 EV plus 0.7 EH, and that should equal 1D plus 0.7 QE plus 0.7 times 0.2 times 1.3 D. Remember, there's a 1 here. I didn't just say 0.7 times 1. So our C is equal 118D plus 0.7 QE. And or we can use the other one too. The other one was C was 1D. What was it? Okay. If we use number 9, these L and S become 0. So 1D plus 0.525 EV. That's not going to control. Plus 0.525 EH. I think this one's controlled. This is better. So we're going to calculate the roof dead load first. And this is like the video I made about seismic. You got to calculate all the weight of the building. And that was given as a 15 pound per square foot. That was given. And then they say the let's say the joists are 12 feet long, times 12 feet long. This is the joist. The and then we're gonna have it to have it to be our wall was 10 feet shear wall. The turbidity dead load and the tension cord was half of that, which was 5 feet. So we're going to divide that by 2. And this should give us 6 times 15 become 90 pound per foot. Then we're going to calculate the wall itself. Wall dead load, which was 20 pound per square foot. And multiply that by a 16 feet tall wall, and that give us 320 pound per foot, and the total comes out to be that total is equal 410 pound per foot. Okay, so now we already calculated QE from above was 5.5, which was 5510 pound. And then the uplift for the dead load is this 410 pound. Remember, that's a pound per foot. You got to convert it time 5 feet. And this 5 feet is that's 1/2 of the shear panel, which was 10 divided by 2, 5 feet. And that will give us 2050 pound, 2050 pound. Then we can go ahead and plug all these numbers in for the load combination. So T comes out to be, from above, 0.42 D minus 0.7 QE, which is equal 0.42 times 2050 minus 0.7 times 5510. So that became this should be 0.7. Already the factor was in there. I forgot about that. So this is going to be minus 5510, and that will give us T is equal 44. No, let's use my calculator here. Minus 4650 pound. Basically, T is equal that much. So one thing you gotta remember, this is an uplift, and when you have a shear wall like this, the 2x8 for this member right here may be adequate strength-wise, but it's not going to be adequate for bolting through. So a lot of time when you look at the shear wall, when you have a 2x, they might double it. You have the two 2x8s, so you're going to have 2 each, or they're going to have a 4x something, whatever they might use. And here also will be doubled, this will be doubled, and this will be doubled, because the tie down right here you need enough thickness for the bolt to really have a grip on something. And I will show you the a picture. Hold on. So when you look at the corner of the shear wall, it's all doubled like this one here, because you need a single 2x stud will not provide enough adequate thickness for the fastening to the anchor bracket. So you need it thicker than one single 2x. You need probably 2 of them, or a 4x member. That way you have a good connection for the tie down. And a lot of time in a construction anyway, they double these corners. So that's what I mean. This cord, we're going to double it too. So let's go back to the writing again. Okay, we're going to jump into a compression cord here. Right here, and dead load was 410, which we already calculated from back here, right there, and multiplying that by the turbo tree width, which is basically half of the shear panel, comes out to 2050, and we already know 0.7 QE is equal to 5510 pound. And dog is barking. So the compression comes out when we do the load combination. We end up with the C is equal 1.18 D plus 0.7 QE. And this, we did this ahead of a time. Remember, there was a 3 load combination, and this one will control. So if we multiply this together and put the number in, we should get 7,930 pound. This is for compression. Now remember, when we did column design, we did a bunch of them. So now we have to treat this like a column. We got to go ahead calculate the the L over D, or K time L over D, and then we have to calculate the both weak and strong axis, and calculate F prime C and calculate CP. So I'm going to go ahead and write those down ahead of a time because that takes a long time. You already know how to do column design anyway. And just watch this going quickly. So this is just like a column design, and there's multiple video I have for column design, and we're going to treat it like that. We're going to find this effective length over D on a strong axis, and we're going to get 26.5. And from NDS 4.31, this is the equation. You know, you've seen this many times. The F prime C is equal FC times CD CMCT CFCP, and then the column stability factor based on NDS at 3.71 is this long equation, which I went over here. We calculate the component for it. E prime is at come out 580,000, and then from NDS table 4A we can find FSC. CF is 1.05 for compression for 2x8, and that's from table 4A. You remember that. Then CD for load combination comes out to 1.6, and this is the equation for F star C without a CP. We multiply those, then we can calculate the CP. Once we calculate the CP, we can go ahead and do the F prime C. So that's what I got here, and let's change the color for good luck here, and that's going to equal 1350 time 1.6 time 1 time 1 and 105, and then time 0.278. So now our F prime C comes out to be 631 psi. That's the compression capacity of compression stress. And remember, we have to make sure the bearing. We also got to check. Let's check the bearing capacity. Which one control? And that's basically a F prime C perpendicular. So we're going to work on this next. Okay, so we're going to go ahead and check for perpendicular bearing, and we done this before. And we have comes out to 625, which is less than 631, which control. They both was almost the same. And if we go ahead and calculate the force, it's going to come out to be almost similar, which is less than our applied load, which was 7930. That way, so 1 is not going to do it, 2 it's going to do it. Therefore, we're going to say, okay, use 2 2x8 studs, and that should take care of it. All right, done.